Hi everybody, Dr. Marty back, and we are going to wrap up Chapter 6, which has been on systems of equations, by looking at linear inequalities. So all the work we've done thus far has been focused on equations, and it turns out you can actually apply the first method that we use for solving linear inequations, which was graphing, to systems of linear inequalities, okay? And so we're going to spend today just learning about how to do that. So before we do that, we have to think about what a linear inequality is, okay? A linear inequality is an inequality. That means it has a less than, greater than, less than or equal to, or greater than or equal to sign, right? Instead of equal. And it's of a line. So here we have y 5x plus 3. This is like y equals mx plus b, but instead of an equal sign, we have a greater than or less than symbol, okay? So the first thing we're going to do is we're going to investigate how we can determine whether ordered pairs are solutions to a linear inequality. That means we're given some kind of linear inequality. Here we have y is less than 5x plus 3, and we're given an ordered pair. And we have to say, is this ordered pair a solution? A solution, okay? So let's see how we would do this. Well, in this case, our ordered pair here is x comma y, right? So all we have to do is we have to plug this in to our equation. I'm going to use some different colors just so you can see how this works. So for y, we're going to plug in 3, right? And that's going to be less than 5 times x is 5x, so it's 5 times 5 plus 3. Okay? Now I'm going to get rid of the color now. So 3 is less than 5 times 5 is 25 plus 3. 3 is less than 28. Now, is this true? Yes, this is true. So that means 5 comma 3 is a solution. I think this is pretty straightforward, right? All we did is we took the x and y, the ordered pair, we plugged it into our linear inequality, and if the inequality ends up being true, we're going to say it is a solution. Let's go down to example 2 at the bottom. We have 2y greater than or equal to 3x plus 4, and our ordered pair is 5 comma negative 3. So once again, we're going to plug it in. I'll use colors again, just to be a little bit clearer. 2 times y is negative 3, right? So 2 times y is greater than or equal to 3 times x is 5 plus 4. Let's solve. 2 times negative 3 is negative 6. Greater than or equal to 3 times 5 is 15 plus 4. Negative 6 is greater than or equal to 19. Is that true? Not true. Okay? So 5 comma negative 3 is not a solution. Does that make sense? Okay? So all we did here is we were given an ordered pair, an x and a y, and we're given a linear inequality. We plug the x and the y in. If, when we plug the x and y in, we solve, we get an inequality that's true, then it's going to be a solution. If we get one that's not true, it's not a solution. So that's how to determine whether ordered pairs are solutions to a linear inequality. Okay, I think that's pretty straightforward, and hopefully that wasn't too hard for you to understand. Now, here's where things get a little bit more interesting. Now we're going to start looking at how we can graph linear inequalities. Okay, so graphing linear inequalities, there's a couple things that we need to know. Okay, so first of all, we're going to be essentially going to be graphing a line, right? But if the inequality is less than or greater than, that means there's no equal sign, no less than or equal to, greater than or equal to, it's just less than or greater than, we're going to use a dashed line, If it's greater than or equal to or less than or equal to, we're going to use a solid line. And this is going to make sense in a bit when we graph, but basically, the less than or greater than and equal to, where there's an equal to, is saying that it's inclusive. It means any point on the line satisfies inequality. The less than or greater than, the dashed line, means it's not inclusive. So if there's a point that's on the line, it does not satisfy. Okay? And then all we're going to do is after we graph the line, we're going to plug in the point 0, 0, or we're going to see there's some cases where 0, 0 doesn't work because it's on the line, and we're going to see if it's true. If it's true, we're going to shade the part of the graph that contains 0, 0. Okay? Shade part of the graph that contains 0, 0. All right, so example number 1, y is greater than x plus 2. Okay, y is greater than x plus 2. Right? So the first thing we got to do is we need to graph it. Okay, so we've got y equals mx plus b as our form, and this is in that form, right? Even though it's an inequality. So our slope is 1 here, right? The coefficient on x is just 1, so our slope is 1, and the y-intercept is 2. So let's go ahead and graph that. So we're going to start with 0, 2, and our slope's going to be 1. But there's something very important to know. Very important to know, okay? It needs to be a dashed line, right? When I look at this, I see it has to be a dashed line because it's a greater than x plus 2. So I'm going to find my points. Slope is 1. We started at 0, 2, so up 1, over 1, up 1, over 1, up 1, over 1, up 1, over 1. We know that's our line. But instead of doing a full line, I'm going to draw a dashed line. So it looks like that. Okay? See how it's a dashed line? Now, this is where it gets a little interesting. Okay? And I'll use colors again to make this a little clearer. Now what we have to do is we have to plug in 0, 0. You can see that 0, 0 is right here. So 0, 0 is on this side of the line. And we got to see if it's true. Okay? If it's true, we're going to shade the part of the graph that contains 0, 0. If it's false, we're not going to shade it. We're going to shade the other side. So let's try that. We have y is greater than x plus 2. Move this over so you can see. I'm going to plug 0, 0 in. Okay? So 0 is going to go in here. 0 is going to go in here. So I've got 0 is greater than 0 plus 2, or 0 is greater than 2. Is that true? Not true. Not true. So that means the side that has 0, 0 is not going to satisfy the equation. So what we're going to do is we're going to shade the other side. So I'm shading above. So that means all of the spots up here, this is shaded, that means all of the spots up here satisfy the equation, and anything below the line to this side does not. Right? Let's try this over here for example 2. Example 2, we've got y is less than or equal to negative 2x plus 1. Okay? Still using y equals mx plus b, so our slope is going to be negative 2. Y-intercept is going to be positive 1. Now notice that we have y is less than or equal to. So that means this is going to be a solid line. Whether or not the line is solid or dashed is really important. You need to know it. Okay? So let's draw our graph. 0, 1 is our point. It's negative 2, so we go down 2 over 1, down 2 over 1, down 2 over 1, down 2 over 1. And you can continue on like this, right? And now we're going to draw our line. It's a solid line this time. Cool. We've got our line drawn. We know it's solid because it's less than or equal to. Now, we have to figure out if we need to shade. So we're going to plug 0, 0 in. Okay? Now I'm just going to do it this time. I'm going to have 0 is less than or equal to negative 2 times 0 plus 1. 0 is less than or equal to 0 plus 1. And we get 0 is less than or equal to 1. This is true. That's true, right? So that means the side that has 0, 0 right here is going to be true. So we're going to shade all of this. Now, some of you might be wondering, why are we shading? Why are we shading? Well, in this case, we don't have a set line. A line would be an equal sign. So for a line with an equal sign, all the points that are on the line would count as satisfying the equation. And we know that when we were doing, for example, systems of inequalities, that where two lines intersect was a solution to both. But in the case of an inequality, we have tons of points that satisfy the inequality, right? It's not just the line, because if it's just the line, that would be y equals negative 2x plus 1. It's also anything that comes up with a y value that's less than negative 2x plus 1. So all of these points over here actually satisfy this inequality. All of these are true. 0, 0 is true along with everything below the line. Over here, everything above the line was true. Let's look down here at example number 3. This one's going to be pretty straightforward. Our line is x is less than, our inequality is x is less than 4. So our line's just going to be on x equals 4, and it's dashed, right? dashed line. So we've got x equals 4. We're just drawing a dashed vertical line. Okay? Makes sense, right? X equals 4 would just be a straight line up here. It's dashed because it's x is less than. Now let's plug in 0, 0 and see what we get. Well, there is no y, so we just plug in 0 in for x. Is 0 less than 4? True. So that means anything on this side is going to be true, so we're going to shade over here. So any value over here is going to be true. We could test this, right? We could pick some value like x equals 5. 5, 5, 0, 5 is less than 4, right? This one's not going to be true. If we put 7, 1 in, we put 7 in for x, that's not going to be less than 4. Okay? So graphing linear inequalities, we are going to figure out what the line is, right? Slope-intercept form is the easiest way to graph. Then, if it's a less than or equal to, we're going to use a dashed line, less than or equal to, less than and greater. If it's less than or greater than, it's a dashed line. I'm sorry about that. It's a Monday morning right now when I'm recording this. Less than or greater than is a dashed line. Greater than or equal to, less than or equal to is a solid line. That's inclusive. We're going to graph that line, either dashed or solid. We're going to plug the point 0, 0 in and see if it's true. If it is true, we're going to shade the side that has 0, 0, like over here. If it's not true, we're going to shade the other side. Okay? So that's how to graph linear inequalities. And then our final thing that we're going to cover, is going to be graphing systems of linear inequalities. Systems of linear inequalities. Okay? Now, in this case, we're going to have two linear inequalities. So this is the same thing we were just doing, but now we're going to have two. And you're going to see that that's going to make this very interesting. And what we're going to find is, just like when we graphed systems of equations, when we graph systems of linear inequalities, anywhere where there's overlap, both of the inequalities are going to be the solution. Okay? So let's see what we got. Once again, greater than, less than is a dashed line. Greater than, equal to, less than, equal to is a solid line. After we graph, we're going to plug in 0, 0. We're going to see if it's true or not true. We're going to shade if it is true. We're not going to shade if it's not. Any areas that are shaded for both are going to be the solution. So let's look at this example number 1. We've got y is less than x minus 1. Y is less than x minus 1. So I'm going to start by graphing this one, and let me use a different color so I'm not confusing you. I'll use green and peach. Green and pink. Okay? So I'm going to do everything for y is less than x minus 1 in green. All right? So first of all, if it were slope-intercept form, our slope would be 1, right? M equals 1. That's a coefficient on x. Our y-intercept would be negative 1. It's a dashed line, right? So let's go ahead and graph that. Y-intercept negative 1, slope is 1. Okay, it's a dashed line. So we're making a dashed line that goes like this. So here's our dashed line. We've now graphed the linear inequality. Now we got to decide which side to shade. So we're going to plug 0, 0 in. So I'm going to plug 0 is less than 0 minus 1. I get 0 is less than negative 1. Is that true? Not true. So that means this side, which has 0, 0, is not going to get shaded. This side is. Okay? So now we've graphed our first linear inequality. Now we have to graph our second one. We've got y is greater than or equal to negative 2x plus 2. Our slope here, m, is going to be negative 2. Y-intercept is going to be 2. So y-intercept 2, 1, 2. Our slope is negative 2. Down, negative down, down 2 over 1. Down 2 over 1, down 2 over 1. You can get the picture, right? We're going to get a line that looks something like this. Now it's a line, right? It's solid because it's greater than or equal to. Plug 0, 0 in. We get 0 is greater than or equal to negative 2 times 0 plus 2. 0 is greater than or equal to 0 plus 2. 0 greater than or equal to 2. Not true. Right? So this side, 0, 0, is not true. That means we're going to shade this side. Okay? So look what we end up with. We end up with a situation where we have one line, the first one, one linear inequality that's shaded down here. We've got a second one that's shaded over here, and that means this area right here, where they're both shaded, is a solution to both. Right? And notice those red arrows point to things that are both shaded. That means that in this area right here, including this line, not including this line because it's dashed, but in here, those are solutions to both linear inequalities. Okay? Let's do example number 2. This is our last one. I'm going to use colors again. Y is greater than 3x minus 4. Okay? M equals 3, B equals negative 4. It's a dashed line. But remember, the dashed in solid is important. Okay? So slope is 3. I'm going to go up 1, 2, 3 over 1, up 1, 2, 3 over 1, up 1, 2, 3 over 1. This is a dashed line. Okay? Plug in 0, 0. 0 greater than 3 times 0 minus 4. 0 greater than 0 minus 4. 0 greater than negative 4. That's true. Right? That's true. And so we're going to shade the side that has 0. Okay? Shade the side that has 0. Hope you can see that. It's a little bit light. Then we got x is less than 2. Well, this is just a vertical line. It's dashed, right? On x equals 2. Plug 0 in. 0 is less than 2. It's true, right? So that means this side gets shaded. I'm going to try to use vertical, horizontal lines so you can see it a little bit more clearly. And that means anything from here to here is going to be our solution set. Okay? So that's how you can graph systems of linear inequalities to solve. With systems of equations, we can graph and we find the point where the two lines intersect. With systems of linear inequalities, we're going to graph, we're going to have shading, and any times where both shading is true, right? Where both the area is shaded with both colors, that is our solution set. So that's all there is to our little kind of mini unit in chapter 6 on systems of linear inequalities. Just as a quick recap, right? If we want to know whether or not a ordered pair is true for an inequality, a linear inequality, we're going to plug both the y and the x in. We're going to solve. If it's true, 3 is less than 28, that's going to be a solution. If it's not true, it's not a solution. This becomes in handy when we plug in 0, 0. Okay? If we want to graph linear inequalities, remember that a dashed line represents greater than or less than. A solid line greater than or equal to or less than or equal to. We're going to draw the line, either dashed or undashed. We're going to plug 0, 0 in. If it's true, we're going to shade the side that has 0, 0, like over here. If it's not true, we're going to shade the side that doesn't have 0, 0. And then to graph systems of linear inequalities, we're just going to graph each linear inequality, make sure we shade, and then find any areas where they're both shaded, and that's going to be our solution. All right, so that's it for chapter 6. We'll be back with new stuff next time.